Blood of God. How do I even respond to these people? All right. Good evening, everybody. Good evening. We are starting in the next 5 minutes or 3 minutes. So let's allow everybody to join. Okay. We're starting in the next 5 minutes or less than 5 minutes. So let people join first. Okay. Lighting is very bad. Very, very bad. Okay. Please do well to share the link so that others can join. Share the link so that others can join. Okay. Good evening, everybody. I'm seeing that. Good evening. I hope you're doing great. How was your day? All right. So share the link so others can join. All right, all right. So please keep joining, keep joining. Once we get to 20, we'll begin the live. We are about 11 for now. Once we get to 20, we'll begin the live. We are just 11. Please share the link so others can join. You make me smile. It's laughable. Unphotographable. But you're my favorite walk around. It's my lyric. When you open it, just think I smile. Don't change the hair for me. Okay, we are 12. Almost there, almost there. We're almost there. Please share the link so others can join, please. Share the link so others can join. Not if you care for me. Oh boy. I don't know why I didn't have this color. I'm trying. Okay. All right, all right. We're almost there, almost there, almost there, almost there. Okay, almost there. Okay, I think we are up to, how many are we now? We are 18. I think we are going to start. We are starting right away. We are starting right away. We are starting right away. Okay. Good evening, everybody. Good evening, everybody. Please bring out your manuals. Let's start from the very first page. So if you have your manual, open to page, let me check for it. You have your manual. Open to experiment 9. Check out experiment 9. Open to experiment 9. That's where we are. Check out experiment 9. So for experiment 9, we are going to be filling these blank spaces here, following the VSEPR theory alongside the theory of hybridization. So we are going to complete this entire table, and that's going to take us about, let's say, 20, 30 minutes. That will not take too long. Then we'll go over to the other questions. So if you are ready, I'm ready. So I'm starting right away. So I'm starting from question number 1. So if you are there with me, I'm about to answer question number 1. Now, look at the nature of the question here. We were asked to fill in the blanks here. So we have molecular geometry, we have molecular formula, we have number of bond pairs, we have number of lone pairs, we have the hybridization of the central atom, we have the molecular geometry, the bond angle, and the dipole moment. All right, so this is actually coming from VSEPR theory. So this is how to do it. First things first, we can draw Lewis structures at this point. So I want to believe if you know how to draw the Lewis structure for BeCl2. If you can't, this is the Lewis structure. You have B, E at the center. Okay, let me use a dark pen. Okay, you have BE at the center. That's the central atom. You have chlorine by the sides. Sorry, it's erroneous. So BE at the center, you have chlorine by the sides. All right, so that is the Lewis structure there. Then you complete the octets of the chlorine. So that's about the theory of Lewis structures. Now, from this Lewis structure we just drew here, now, how many bonding pairs do you have around the central atom? There are 2 bonding pairs, 1 and 2. Don't forget that a dash represents a bonding pair. So we have 2 bonding pairs there. So let me fill in my blanks. So I have 2 bonding pairs for that. So this is number of bond pairs. I have 2. Now, how many lone pairs are here? Now, from the drawn Lewis structure, there is no lone pair on the central atom. So we have 0 there. All right, so what about the hybridization? Now, this is just a very short trick. Anytime you've drawn your Lewis structure and you notice that around the central atom, you have 2 pairs, just 2 pairs, whether bonding or non-bonding, the hybridization is going to be SP. Now, I talked about this in class some time ago. So in case you did not attend that class, let me repeat myself. Now, check this out. If you have 2 pairs of electrons around the central atom, the hybridization is going to be SP. Now, these 2 pairs I'm talking about, they could be bonding pairs, they could be lone pairs. But what matters is you have 2 pairs of electrons around the central atom. The hybridization is SP. Now, if you have 3 pairs of electrons around the central atom, the hybridization is going to be sp2. All right. Now, if you have 4 pairs of electrons around the central atom, your hybridization is going to be sp3. Now, if you have 5 pairs of electrons around your central atom, your hybridization is going to be sp3d. And if you have 6 pairs of electrons around the central atom, your hybridization is going to be sp3d2. So that is all about this experiment. That's for the first page. So these are the basic things you need to understand. So these are the number of pairs of electrons you need to have before you can talk about sp. And don't forget, the hybridization we are talking about here is with respect to the central atom. With respect to the central atom, don't forget. Okay, so I want to be sure you're all following me. Are you all following me? Are you following me? If you're following me, say hi. Say hi on the group. Let me see. Say hi on the comments. I want to say that. If you're with me, say hi. All right. You're with me. Now, let's move on. I want us to be very, very fast today. So let's now go straight to filling the blanks. So what will be my hybridization for for BeCl2 based on the Lewis structure I drew? What will be my hybridization? Don't forget, I have just 2 pairs of electrons around the central atom. So that means that my hybridization is going to be sp. Very simple, sp. Moving on now. What will be the molecular geometry? According to VSEPR, anytime you have 2 pairs of electrons around the central atom, according to VSEPR, and you have those 2 pairs of electrons are bonding pairs, the best possible arrangement is going to be linear. All right, so all linear molecules are expected to have sp hybridization around the central atom. So it's linear. Now the bond angle is going to be 180 degrees. 180 degrees. And dipole moment. Don't forget, anytime you draw a Lewis structure, the very first method of knowing whether that Lewis structure, let me say whether that structure is polar or non-polar, or if that structure has dipole moment or not, the very first method of identifying that is by checking out the central atom. If the central atom does not have any lone pairs, if there is no lone pair of electron on the central atom, it is 100% significant that that molecule does not have dipole moment, which simply means that that molecule is non-polar. Take note. Now, looking at this now, the central atom does not have any lone pair of electrons around the central atom. So therefore, dipole moment, we are going to say no. It does not have dipole moment. Now let's go to the next one. For the next one, the molecule there is called boron trifluoride, BF3. If you draw the Lewis structure, it looks just like this. You have B, you have F, you have F, you have F. That's the Lewis structure there. Then put it in a box so you don't mix it up with the other one. So that's the Lewis structure we have for BF3. Now for the BF3 molecule here, don't forget you complete the octets of the terminal, or let me say the terminal atoms. Yes, complete the octets of the terminal atoms. Now, if you are confused on how to draw Lewis structures, check out my video I posted, I think, a couple of weeks ago on Lewis structures. There is a playlist I created on my channel here. It's called Mastering Lewis Structures. Check it out. So you see how to draw Lewis structures from there. So hoping that you can draw Lewis structures, this is how to draw the Lewis structure for BF3. Now, from this Lewis structure, let's check it out. How many bonding pairs are there around the boron? How many bonding pairs are there? 1, 2, 3. There are 3 bonding pairs. So I'll just go to my box and write 3 bonding pairs. How many lone pairs are there? Now, you can see from this Lewis structure, there are no lone pairs of electrons around the boron. So therefore, I'll write 0. All right, so moving on. What is the hybridization? Now, let's go back to this chart I showed you earlier. Since I have barely 3 electron pairs around the central atom, it is going to be sp2 hybridized. So it is sp2 hybridized. So what about the molecular geometry? Now, don't forget, The molecular geometry here is going to be trigonal planar. According to VSEPR model, it is trigonal planar. Trigonal planar. All right, so that's the molecular geometry there. What about the bond angle? According to VSEPR, it is 120 degrees. Now, don't forget what I told you earlier. As far as there is no lone pair of electrons around the central atom, this particular molecule here is non-polar, or you can say that it has a zero dipole moment. So we are going to write no here. It does not have dipole moment. So let's move on to the next one. The next one is SnCl2, that is tin dichloride. Now, this molecule is very tricky. I don't want you to browse anything about it. I want you to draw the Lewis structure all by yourself. Now, tin dichloride, now check out the group number for tin. Tin is found in group 3. Tin is found in group 3. So this is how to do it. So tin is in group 3. Okay, plus. So since tin has 3 valence electrons, chlorine has 7 times 2 is 14. Please check well, check well. What do we have here? I want to be sure. Tin is in group 3. Okay, check. Yeah. I hope I'm correct. Is tin in group 3? Verify. I want to be sure you're following me. Is tin in group 3? Is tin in group 3? I need answers in the comments. I want to be sure you are with me. I'm still waiting. Is tin in group 3? All right, verified. I need one more, yes. I need one more person to verify that. Is tin in group 3? Gloria Bassi just verified. Yes, okay. I can see Felicia, okay, and Diana, okay, and Diana. All right, that's great, that's great. In group 3. So we have 3 and we have 14. So everything gives us 17. So what's our central atom? Is tin, Sn. Please check this out. Tin, central atom. Now put your chlorines by the sides. Wherever, okay. So first things first, an electron pair in between. Now complete the octets of the terminals 1, 2, 3, 4, 5, 6 plus this 2, 8. 1, 2, 3, 4, 5, 6 plus this 2, 8. How many electrons are remaining here? Just 1. All right. Guess what, guys? This is the Lewis structure for tin dichloride, SnCl2. So what does this tell you? Now this tells you that this molecule you are seeing here, I think there is an error. Let me check something here. 714, 317. Let me verify something. Be right back. Okay. Okay. We're having an odd number there. I think there's an error. So check this out. Tin should be in the same group with carbon and silicon. So tin is in group 4. So that's a mistake there. So tin is in group 4. Tin is in group 4. So we're going to have a total of 18 electrons here. All right, so 18. All right, so we're going to have a total of we're going to have a lone pair around the tin. So from our Lewis structure, it is very obvious that for tin dichloride, we have a total of 2 bonding pairs. What are the 2 bonding pairs? 1 and 2. Those are our 2 bonding pairs. We have 2 bonding pairs there. How many lone pairs are there? Now, don't forget that a lone pair is made up of 2 electrons that are not participating in a bond. So therefore, there is a lone pair here. We just have 1. So how many lone pairs are there? 1. What will be the hybridization? Don't forget, anytime you have a total of 3 electron pairs around the central atom, it is going to be sp2 hybridized. Don't forget, as far as the total number of electrons is equal to, or electron pair is equal to 3, it is going to be sp3 hybridized. So sp2 hybridized, sorry. All right, so we are done with that. So what will be the geometry? What will be the geometry for tin dichloride? The geometry here, according to VSEPR, is going to be bent or angular. So please, you can choose just one. Don't write the two. So the geometry is bent or angular. So what will be the bond angle here? Now, if you don't mind, you can write this down. It's very important you write this down. It's very important you write this down. It's very important you write this down. Write this down, please. Regarding the bond angle, it's very important you note that lone pairs take up more space than bonding pairs. Take note, write it down. Lone pairs take up more space than bonding pairs. So anytime a lone pair is present on the central atom, it tends to push the geometry. For example, look at this thing. This thing naturally is supposed to be a straight molecule. Lone pair here, the lone pair tends to push the geometry. That is why you have tin looks like this. All right, so tin now looks bent because of the presence of what? This lone pair here. Now it's very important you note this. All right, okay, so the geometry is now what? Bent. So anytime a lone pair is present, it tends to push the geometry. Very, very important. So I want to believe you've written that down. So now, since the geometry has now somehow distorted, it is very obvious that the bond angle is going to change. Now, how is the bond angle going to change? Don't forget that the ideal bond angle, whenever you have 3 pairs of electrons around the central atom, is supposed to be 120 degrees, according to VSEPR theory. But now, since you have a lone pair here, a lone pair tends to what? Distort the geometry, thereby making the bond angle to deviate. Now, the bond angle deviates lower, not higher. It goes down. And the degree of distortion, we don't really know because VSEPR does not state that. So because of that, we are going to write that the bond angle for SnCl2 here is going to be less than 120 degrees. Now, to search for the bond angle of SnCl2. If you search for it, you are still going to see that the angle is going to be less than 120. But since VSEPR does not specify that, we are going to write less than 120 degrees. Okay, now let me ask you, is there going to be dipole moment here or not? So I should drop the answer in the comments. Is there going to be a dipole moment or not? Dipole moment, yes or no? Let me see. Let me see your responses. Correct. The answer is correct. Yes, there will be dipole moment. Why? Because of the presence of this lone pair. So I told you earlier that the best way to identify whether a molecule will be polar or not is, number one, if the molecule does not have lone pairs on the central atom, then that molecule will be non-polar. But if the molecule has at least a lone pair, it's going to be polar. But there are conditions attached. You are going to meet all the conditions in this subject. All right, so the answer is yes, it is polar. It has dipole moment. Let's go to CH4. Now, CH4 is a popular organic compound. The structure looks like this: C, H, 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 H. All right. Now, the molecular geometry for CH4 is going to be tetrahedral. Now, how many bonding pairs are here? 1, 2, 3, 4. How many lone pairs are here? 0. Is this molecule going to be polar or non-polar? The answer is what? It's going to be non-polar. All right, so I think we are done with this one. Let's just fill in the blanks. So CH4, number of bonding pairs is equal to 4. Number of lone pairs is equal to 0 because around the carbon atom, we don't have any lone pairs of electron. All right, so what about for the hybridization? Don't forget, anytime you have 4 electron pairs around the central atom, don't forget this table here. we are going to say it is what? sp3 hybridized. So the hybridization is sp3. All right, so we have geometry there, tetrahedral. All right, tetrahedral. All right. So let's move on to the next one. So what's the bond angle for a tetrahedral molecule? The bond angle is going to be 109.5 degrees. This is the bond angle for a tetrahedral molecule. So what is the dipole moment? Yes or no? The answer is what? No. It is not polar. Move on to the next. Ammonia, NH3. What is the Lewis structure for ammonia? Now look at ammonia here. Ammonia, nitrogen central. The hydrogens are terminal atoms here. Now for ammonia molecule, there is a lone pair on the nitrogen. So we can see that there are a total of 4 electron pairs here. 1, 2, 3, 4. Out of the 4 pairs, how many bonding pairs are here? 1, 2, 3. How many lone pairs are here? 1. So we can say that there are 3 bonding pairs and you have 1 lone pair. Now, what will be the hybridization? It still remains sp3 because we have a total of 4 electron pairs around the central atom. What would be the geometry? According to VSEPR model, the geometry is going to be trigonal pyramidal. Trigonal pyramidal. What is the bond angle? Now we don't know the bond angle. Do you know why we don't know the bond angle? Because of the presence of this what? Lone pair. Now don't forget that the lone pair tends to distort the geometry. A lone pair takes up more space than a corresponding bonding pair. So what does that mean? That simply means that the bond angle is going to deviate lower. If you check for the real bond angle for NH3, is about 107. But we are not going to write 107. But what we're going to write here is what? We're going to write is going to be what? Less than 109.5 degrees. That is VSEPR. We are trying to follow VSEPR theory. Okay, now is it going to be polar or non-polar? Dipole, yes or no? Let me see your responses now. Dipole moment, yes or no? Dipole moment, yes or no? Dipole moment, yes or no? Yes, from Precious Ebe. Yes, Precious Ebe, yes. So dipole moment is yes. Okay, you guys are doing great. I love what you're doing. All right, so now let's go to water. Now look at water molecule here, H2O. This is Lewis structure for water. Okay, seems this paper is already messed up. Let me pick up another one. All right, let's use this one now. So this is water here. You have O central, H, you have H. All right. So this is water here. There are 2 lone pairs on the oxygen atom. Now look at where the 2 lone pairs are oriented. They are oriented at the top, not down. So total number of pairs of electrons here, we have 1, 2, 3, 4. Out of the 4 pairs, how many pairs are bonding pairs? Just these 2. So we're going to write total number of bond pairs is what? 2. How many lone pairs are here? These 2 here. So we have 2 lone pairs. So 2 bonding pairs and 2 lone pairs. All right. So let's get to hybridization. It still remains sp3. So it is sp3 because we still have a total of 4 electron pairs around the central atom. Okay, so what about the geometry here? It is what? Bent or angular? Now, another question. What is the bond angle? Now, the ideal bond angle, if you check the bond angle online or in chemistry tables, you discover that the bond angle is about 104.5 or 105. What does that mean? That simply tells you that a lone pair takes up more space and makes the bond angle to go lower than the original when all the bonds are complete. So what we have here is going to be less than 109.5 degrees. Dipole moment, yes or no? Let me get your responses on the comments. Dipole moment, yes or no? Dipole moment, yes or no? Okay, Conradi, yes. Precious Ebe, yes. Okay, I can see I can pronounce this. Yes. Felicia, yes, thank you. You guys are doing great. Yeah, it is yes. So that is the main reason why we normally say water is polar. Let's complete it now. I think we're almost done with that. Let's complete it. Now we are now on the next molecule. Which is, let me check my manual whether I can find that. Let me check whether I can find that. Oh, I can't find that. Let me check. Someone should drop the next molecule in the comments. Drop the next molecule in the comments. You are done with water. Let's drop the next one there. What's the next molecule? Check your manual. I want to be sure you're following. Drop. Okay, PCl5. That's beautiful. PCl5. So PCl5. That's the next molecule we're going to be talking about. So for PCl5, let's draw the Lewis structure for PCl5. So look at PCl5 here. Now, all these Lewis structures have been drawn already in my video. So if you check my previous videos on drawing of Lewis structures, in fact, everything about Lewis structures, you can find them there. So look at PCl5. P, Cl, 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 Cl. This PCl5 here. Now, the octets of the chlorine atoms are complete. Now, this is an example of a molecule in which the central atom disobeys the octet rule. Now, the phosphorus atom here is carrying more than 8 electrons. If you count, look at it. 2, 4, 6, 8, 10. It's carrying 5 pairs of electrons instead of 4. So that's an example of an exception to the octet rule. So how many bonding pairs are here? How many? We have 5 bonding pairs. How many lone pairs are here? The answer is 0. No lone pair is here. And this is a clear indication that this molecule is going to be non-polar. So dipole moment is going to be what? No, not yes. All right. What about the hybridization? The hybridization is going to be sp3d2. Oh, sorry, sp3d. We talked about that earlier. All right. So how many bonding pairs are here? 5. How many lone pairs? 0. What is the hybridization? sp3d. All right. So what is the molecular geometry? Now the molecular geometry is going to be what? Trigonal by pyramidal. So trigonal bipyramidal, that is going to be the molecular geometry. So what about the bond angle there? The bond angle, we have 2 bond angles for a trigonal bipyramidal molecule. We have 90 degrees at the axial plane and 120 degrees at the equatorial plane. So we have 90, 120. So that's the bond angle here. So what about the dipole moment? It is what? No, not polar, because there are no lone pairs on the central atom. Let's go to the next one. Someone should drop the next molecule in the comments. Next molecule in the comments. You are doing very well. I can see your comments. You are doing fantastic. All right, SF4. I love that. So we have sulfur, SF4, sulfur tetrafluoride. Let's draw the Lewis structure for sulfur tetrafluoride. Now, for sulfur tetrafluoride, how many bonding pairs are there? Look at sulfur tetrafluoride here. You have S central. You have F. You can see how easy it is for me to draw these Lewis structures. You can also draw Lewis structures like this. So this is sulfur tetrafluoride. Now, there is a lone pair on the central sulfur atom. There's a lone pair there. Now, from this Lewis structure, don't forget, from the Lewis structures I'm drawing today, I am simply ignoring all those dots on the terminal atoms. They are not important because I don't need them. But when you are drawing your Lewis structures, it's very important you put them into consideration. But after drawing your Lewis structures, you won't need to be using them anymore, because if you check out what I'm doing now, I'm simply focusing on all the electrons which are associated with the central atom. All right, so how many bonding pairs are here? 1, 2, 3, 4. How many lone pairs are here? 1. So I have 4, 1. 4 bonding pairs, 1 lone pair, and I'm done. All right, so what about the hybridization? The hybridization still remains what? It remains sp3d. What about the molecular geometry? According to VSEPR model, the molecular geometry here is seesaw. 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 Or you can use seesaw or distorted tetrahedron. So that's the molecular geometry there. All right, let's go to the bond angle. Now, the bond angle is supposed to be 90, 120, but don't forget that there is a lone pair here. So therefore, so simply write less than 90 degrees and what? 120 degrees. We are done. Now, what's the dipole moment going to be? Yes or no? I'm waiting for a response in the comments. Dipole moment, yes or no? Okay, Patrick Vincent, yes. Patrick Vincent, yes. Dipole moment, yes or no? Precious Ekbe, you retracted your message. All right. Okay. All right. Okay, the answer is yes. So the dipole moment is yes. Yeah, so it has a dipole moment. Let's go to the next one. So I want you to drop the next molecule in the comments. Drop the next molecule in the comment. Let's see. Drop the next molecule in the comments. That is beautiful. BRF3. 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 All right. So let's draw the Lewis structure to see. So for BRF3, our central atom is Br. So we have our F. We have our F. We have our F here. Check this out. So for BRF3, this is Lewis structure for BRF3. Okay, we have 2 lone pairs on the bromine atom. There are 2 lone pairs here. Now let's check this out. So how many bonding pairs are here? Let's count. How many bonding pairs? How many bonding pairs are here? 1, 2, 3. How many lone pairs are here? 1, 2. Let's write it down. So we have 3 bonding pairs and 2 lone pairs. All right. So, all right. Talking about the hybridization, it still remains sp3d. All right. What about the geometry? The geometry here is going to be T what? T-shaped. So it has a T-shape. T-shape is the geometry there. T-shape. What about the bond angle? It still remains less than 90 degrees, 120 degrees. All right. So what about the dipole moment? Yes or no? Let me get your answer in the comments. Yes or no? I love what you're doing. Sir, please, I thought the hybridization of SF4 is supposed to be sp3. No, it's not sp3. It's not sp3 because SF4 has a lone pair of electrons. It has a lone pair of electrons on the central atom. So it's not sp3. It is sp3d. All right. Yes, I love that. So the answer is what? Yes. So dipole moment, yes. Let's move on to the next molecule now. Drop the next molecule on the comments. Let me see. XEF2, beautiful. Thank you, Henry Enobon. XEF2, that is xenon difluoride. So for xenon difluoride, what is Lewis structure? Let's draw it together. Xenon difluoride, F2. So Xe, central atom, you have F by the sides. Now check this out. Okay, since this paper has a lot of dots, I want you to see what I'm doing. So Xe, F, and F. All right, now check this out. Now, this particular molecule here, it has 2 lone pairs at the top and a lone pair down. If you draw the Lewis structure, you get to see this. So the total number of electron pairs around the central atom is 5. That is 1, 2, 3, 4, and 5. Now, out of these 5 electrons here, 5 electron pairs, only 2 pairs are bonding pairs. Let's complete that. So we are going to have that. We have 2 bonding pairs and we have 3 lone pairs. Let's come back to the hybridization. Total is 5. It remains sp3d. Let's go back to the geometry now. What is the geometry according to VSEPR? According to VSEPR theory, The correct geometry for XEF2 is linear. Is what? Linear. So we have linear. Linear. Please don't say because it's linear, you want to change this to SP. It's not going to be correct. So this is the only linear molecule that is sp3 dehybridized. Let's move on to the angle. The bond angle in this case is going to be 180 degrees. Why is it 180 degrees? Because experimentally, it has been determined that the two lone pairs at the top exert equal magnitude with the lone pair that is down. Check this out. The two lone pairs up here has the same magnitude with the pair that is down. So because of that, they cancel out. They cancel out. So meaning that this molecule here is going to be what? It's going to be what? 180 degrees bond angle. It's going to be straight. Now, talking about the dipole moment, based on my explanations, is it going to be yes or no? I'm waiting for your response. Dipole moment, yes or no? Conradi, I don't know whether this yes is for yes or no. Okay, Esther F. Young said no. Okay, Henry Nobon said no. Precious Ebe said yes. Okay, now the correct answer here is no. Dipole moment is equal to no. This molecule is not going to have any dipole moment. Why? Because like I said, the lone pairs of electrons cancel out. Check this out. The two lone pairs at the top. Are you with me? So the two lone pairs at the top will cancel out the lone pair that is down, meaning that the lone pair does not even exist in practice. So this molecule does not have dipole moment. Now let's go to the next one. Drop the next molecule on the comments. Let me see. Drop the next molecule on the comment. Let me see. Drop the next molecule on the comments. Let me see. SF6. Beautiful. SF6. SF6. Now let's draw the Lewis structure for SF6 to see whether let's see our assumptions from here. So we have SF6. So for SF6, central atom remains S. So you have your fluorine atoms at the top. I want to be sure you are seeing what I'm writing. If you are seeing what I'm writing, please indicate by writing, yes, I can see it. Can you see what I'm writing? Can you see what I'm writing? Indicate, let me see. Yes, beautiful, beautiful, beautiful. I can see that. All right, let's move on. So I have F. All right, I have F here. I have F here. Okay, I have F here. Thank you, thank you, thank you. That's beautiful. I have another F here. All right, check this out. Check this out. Now, this is the Lewis structure for what? SF6. So from this Lewis structure, we have that there are 6 bonding pairs. Look at it. There are 6 bonding pairs. 1, 2, 3, 4, 5, 6. You don't have any lone pair there. So you have 6 bonding pairs, 0 lone pairs. All right. The hybridization remains sp3d2. sp3d2. What about the geometry? Geometry is what? Octahedral. The bond angle here is what? 90 degrees. All right. So what about the let's talk about the dipole moment. Yes or no? Let me see your answers in the comments. Yes or no? Dipole moment, yes or no? Dipole moment, yes or no? Yes or no? Conrad said yes. MK Junior said no. Felicia, no. Tiene, oh God. Precious Ebe said no. 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 Okay. Yes. Okay. All right. Okay. All right. So the answer is no. Don't forget what I told you earlier. Anytime you don't have, pay attention, anytime there is no lone pair, on the central atom, anytime you don't Pay attention. Anytime there is no lone pair on the central atom, the dipole moment is going to be what? 0. All right, it's going to be 0. So therefore, what we have here is that the answer is no. It's no. So someone should drop the next one. I think it seems I saw a question on the comment. Somebody is asking, why is it, I thought it should be less than 90. No, it should not be less than 90 because there are no lone pairs. There are no lone pairs. All right, IF5 is the next one. There are no lone pairs here, so it can't be less than 90. So IF5 is the next one. IF5. Let's draw IF5. Check this out. Look at IF5. Everybody look at this. Look at IF5 here. So if you want to learn how to draw these Lewis structures, please check out my video on how to draw Lewis structures. It's in a playlist titled Mastering Lewis Structures. You find all those videos there. You check it out. You can draw any Lewis structure of your choice. IF5. Central atom is I. So you have your F, 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 F. And there is a lone pair on the iodine atom. Iodine is our central atom, iodine. So if you check this out, you notice that there are 5 bonding pairs, 1, 2, 3, 4, 5. And there is a lone pair on the central atom. So we have 5 bonding pairs, 1 lone pair. It still remains sp3d2. What about the geometry? Geometry here is going to be what? Square. According to VSEPR theory, it's going to be what? Square pyramidal. Square pyramidal. And the bond angle is going to be what? Less than 90 degrees because of that lone pair there. Now, dipole moment, yes or no? I'm waiting for your response. Okay, somebody's saying, I don't really understand this dipole moment. Okay, I'm going to do a separate video on dipole moments. I'm going to do a separate video on dipole moments, then you will understand it better. But for now, let's just do this assignment, all right? So what is the dipole moment going to be? Yes or no? Wow, there are so many yeses here. All right, so the answer is what? Yes. It will have a dipole moment because the central iodine atom has a lone pair of electrons. So these are just simple tricks on how to identify, how to identify molecules that are polar and the ones that are non-polar. Let's go to the last one. Drop the next molecule for me. Let's see. Drop the next molecule for me. Let's see. Drop the next one. And that's the last for this segment. Then we'll go to the next question. XEF4. Yeah, xenon tetrafluoride. XEF4. XEF4. Now, all right. Let's draw the Lewis structure for XEF4. Now for XEF4, it looks just like this. You have XE at the center, you have F here, F here, F here, F here. Now, for this Lewis structure, you have a lone pair on top of what? XE, and another lone pair below XE. Now, this particular structure is very, very special. Check it out. Remember, I told you that anytime a structure has a lone pair, it is expected to be polar. But the case here is going to be different because of the positions of the lone pairs. So one is up and one is down. Don't forget that the arrangement of these pairs are going to be in harmony with VSEPR theory. Now, VSEPR predicted that the right arrangement for this is going to be square planar. Square planar. So square planar molecules, you have a lone pair up and a lone pair down. And guess what? The two lone pairs have equal magnitudes and they are going to cancel out. And because of that, this molecule here is going to be what? Non-polar, meaning that its dipole moment is not going to be yes. It's going to be what? No. So let's start answering from there. So the dipole moment for XEF4 is going to be no. So the two lone pairs on top of xenon, they both cancel out. All right, let's now go over to this. Okay, the angle here is less than 90 degrees. What about the shape, molecular geometry? It is square planar. Square planar. The hybridization remains sp3d2. How many bonding pairs are there? 4 bonding pairs. How many lone pairs are there? 2. Now, have you noticed something about this table? This table is the same as the VSEPR table I gave you in class. So if you attended my class on this particular topic, you notice that this table you are seeing here illustrates VSEPR theory. Look at it. This is VSEPR theory. That table I gave you in class, this is the table. Look at it. Look at it. The table we used to sing a song. I'm seeing a question here from Conradi. Conradi said, yes, it has a dipole moment. The answer is no, it does not have a dipole moment. It does not have a dipole moment. Dipole moment is equal to 0. It does not have a dipole moment. Conradi, take note. Yes, take note, Conradi. Okay, so this is just the summary of the VSEPR table we did in class. Check this out. Okay, so let's move on to the next question. Let's move on to the next question. It seems I don't have the question. Let me just check my phone and extract it. I don't have the question here. Let me check my phone, then I can extract it. Let's continue. So now let's check out the let's check out the second question, question number 2. I want to believe you are all there. Question number 2 says, it's not clear here. It says, from your models of SF, is that SF4 I'm seeing there? For your models of SF4, BrF4 minus, and XEF4, deduce whether atom arrangements called geometric isomers are possible. And if so, sketch them, indicate the preferred geometry for each case, and suggest a reason for your choice. Indicate which structures have dipole moments and show their directions. Now, let's do this together. So there are about 3 molecules presented here. So let me draw them. There are about 3 molecules presented here. There are about 3 molecules presented. So we are done with this. We've done justice to this. So there are about 3 molecules presented here. Let's look for them. So the first molecule here is SF4. We have SF4. We have another one. We have BrF4 minus. That is not just BrF4. It's BrF4 minus. Take note. Then we have another one. We have which one do we have? We have XEF4. Now look at what the question is asking. Is asking whether we have geometric isomers. Now, all these compounds you are seeing here can never exhibit geometric isomerism. It's not possible. That's number 1. Then number 2, we are asked to sketch them, but we are not going to sketch them because they don't have geometric what? Isomers. No. The question has a charge. It's an error. See, I have the original manual here. It's an error. It's a typographical error. It has a charge. There's a charge there, minus. There's a minus charge there. Take note. Because if you don't put the minus charge there, you are going to have an odd number of electrons, which is not correct. So this is BrF4 minus, not BrF4. Take note. All right. So what about, let me see. So what we're going to do for this particular question is this. So we are going to draw the structure for SF4 in the box. Look at that box you're seeing there. So inside that box, draw this. Check this out. Draw this. And look, check. Now you're going to draw this with respect to the dipole arrows. Check this out. So this is SF4, S. Now you have your F. Check this out. So we are going to indicate the dipole arrows now. We are going to draw this inside that box there. Check this out. Now, between fluorine and sulfur, which one is more polar? Or which one is more electronegative? The answer is what? Fluorine. So Do this for me. The dipole arrow goes down. It goes down. It goes down. It goes, okay, it follows fluorine. It follows fluorine. Don't forget that there is a lone pair here. All right. Now, from this structure you just drew here, you have indicated that there is going to be a net dipole. But guess what? The net dipole is not going to come from here because all these dipoles are going to what? Cancel out. So the net dipole is as a result of the lone pair. So now, you now go to this other side. Go to the dipole moment box and write that the net dipole is as a result of the lone pair on the sulfur atom. So the net dipole is as a result of the lone pair on the sulfur atom. So because of that, that's what makes this molecule to be polar. But somebody else can still argue and say, why don't I just draw this? Maybe just draw sulfur here, draw sulfur, maybe just put all the fluorines down, just like this. That doesn't really make sense, but some people still do this. F, 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 F. Then you put this here. Then you see the person doing this, doing this, doing this, and doing this. And in the end, the person will say that the direction is down. If you do something like this, it's still not bad, still okay. But in the end, it still shows that this molecule has net dipole moment. But don't forget that the reason behind the dipole is because of the lone pair of electrons on the sulfur atom. So you can draw any of this. Any of this. This can be pardoned. This can be pardoned because you're trying to illustrate dipoles here. This can be pardoned. You can draw this. It's fine. You can draw this. You can draw this. Both of them are correct. But if you are drawing this, this is the reason you are going to give. You can say that the net dipole has a downward direction. It has a downward direction. That's if you are drawing this. But if you are drawing this, you stick to the what? The lone pair. That's the most preferred answer. So let's move on to the next one. So there are about 4 boxes here, or sorry, 3 boxes. So on the second box, you are drawing for BrF4 minus. You are drawing for BrF4 minus, Br. I think let's try drawing that Lewis structure. BrF4 minus. BrF4 minus. Br is in group 7. So 7 plus F is in group 7. 7 times 4 is 28. 28 plus 7 is 35. Plus 1 is equal to 36. So this gives us 36 valence electrons. So from here, central atom is B. Sorry, Br. Then you can just say F, 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 and F. All right, so 36, you have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So you have 8, 8, 8, 8. That's 32. You have 2 more remaining. 1, 2, 3, 4. So now what have you noticed here? Have you seen that the arrangement of electrons here, or let me say this molecule, or let me say this PC you are seeing here, will have a square planar shape. Go back to the previous thing we just did. Don't forget that 4, 2, look at it. 4, 2 gives us square planar. And the molecule that is square planar, the dipole moment is going to be what? 0. It will not have any dipole moment. All right. So for this molecule, after drawing this inside the box, make it very small. You allocate your dipole arrows like this because fluorine is more negative. So all the arrows will point towards fluorine. Make it very neat. Now, you can see that the dipoles cancel out on opposite sides. They cancel out on opposite sides. The lone pairs cancel out as well, rendering this molecule, or let me say, rendering this PC here to be non-polar. All right, rendering this species non-polar. All right, so I have drawn my diagram. This is my diagram here for BrF4 minus. Check it out. BrF4 minus. That's my diagram there. BrF4 minus. Then the next thing we are going to do is that we are going to write the reason. Now, what's the reason behind that? Why is it that it does not have dipole moment? Okay, now why does it not have dipole moment? Now, you're going to write, all right, so the net dipoles cancel out. That's the reason. The net dipoles cancel out. The net dipole. Please, are you all with me? Can you hear me? Please, if you can hear me, please indicate. I want to know. I want to be sure you're following. Are you following what I'm doing? If you're following, reply, I'm following. I want to see it in the comments. I'm following. Are you following? Respond, I am following. Okay. Okay, I'm seeing questions here. Now, if you are drawing this, please use a black pen or use a blue pen. But before you use a pen to draw this, make sure what you are drawing is correct. Because once you've drawn, you cannot erase. That's if you're using a pen. So use a pen if you are sure of what you are drawing. But if you are not too sure what you are drawing, use a pencil. So if you make mistakes, you can correct. Then after correcting, pay attention, after correcting the mistakes, you can now use a pen and now make your work to be permanent. So, but in the end, you're going to use a pen to draw this. But for a start, use a pencil. For a start, use a pencil. So your work can be clean. So I think we are done with the three of them. So we've drawn for SF4. So for SF4, what was the conclusion for SF4? Please check this out. For SF4, okay, for SF4, what is the preferred geometry? I'm sure you can fill in the blanks there. For SF4, what is the preferred geometry for SF4? Now you go back to the first question we solved. What is your preferred geometry for SF4? The answer is what? Seesaw. So you write it down there, seesaw. So what is the preferred geometry for SF4? It is what? Seesaw. Now, what is the reason? Now, the reason you're going to give here could also be the reason for the dipole moment. It's still fine. So what is the reason? I've already given the reason here, right? The net dipole is as a result of the what? The lone pairs on the sulfur atom. So dipole moment, yes or no? You're going to write it has a dipole moment. Then for the BrF4 minus, for the BrF4, that is second molecule there, for the BrF4 minus, so what is going to be the preferred geometry? The preferred geometry for BrF4 minus is going to be square planar. It's going to be square planar because it has 4 bonding pairs and 2 lone pairs. So square planar, that's the preferred geometry. Now, what is the reason? Let's check this out. Okay, the reason is going to be as a result of the dipole moment here, okay? So you're going to say that the net dipoles cancel out. Now, the reason you are writing this under the reason. So the net dipoles cancel out because of the square planar arrangement of electrons, of electron pairs. Because of the square planar arrangement of electron pairs. All right. So that's the reason you are going to give there. Now, for the dipole moment, I'm going to say it does not have a dipole moment. It does not have any dipole moment. All right. Now, for the last one there, which is XEF4, let me check. XEF4, yeah, that's it, XEF4. Now, for XEF4, have we drawn for XEF4 today? Let me check. Okay, we've not. We've not drawn XEF4. Okay, let's draw XEF4 now. Let's draw XEF4 now. What did I draw before? I drew SF4. I drew, okay, yeah. So let's draw XCF4. We've drawn it today. There is only drawing it again. We've drawn it today. So look at XCF4 here. XE, F, 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 F. Look at XCF4. There's a lone pair here. There's a lone pair here. All right, so preferred geometry is what? Square what? Planar. That's the preferred geometry, square planar. So what about the reason? Okay, so the reason for the preferred geometry or the reason for the dipole moment, can use any of them. So the reason for the dipole moment here is what? Because it's going to have a zero dipole moment. In fact, let's start from the dipole moment now. Under the dipole moment, right, it has a zero dipole moment. It has a zero dipole moment. It has a zero dipole moment. So why does it have a zero dipole moment? You can now state it clearly. Now, don't forget you're going to draw this particular structure. And after drawing it, endeavor to draw your dipole arrows to be facing the word fluorine. This is similar to what you've drawn before. You've drawn this before for BrF4 minus. You've drawn it before. It's similar to that. Okay. So you can just say the dipoles cancel out due to the square planar arrangement of electrons. Yeah, that's the answer. So the answer is the dipoles cancel out due to the square planar arrangement of electrons. Write it down, please. Write it down. That's the answer to that question. That's the answer to that question. All right, I think we are getting there now. So we are now going to question number 2. Let's go to question number 2. Question number 2 says, I hope you're with your manuals, right? Let's go to question number 2. Who has questions to ask? Let me see. Beautiful, beautiful. Somebody is asking the reason for the SF4 geometry. I thought I provided the answer to that question today. The reason for the SF4 geometry. Let me check. I think I've done that now. Yeah. The net dipole is as a result of the what? The lone pair on the sulfur atom. So let's go to question number 2. It says, predict the structure of the following ions and state the hybridization of the central atom. We are going to be very, very fast now. We are going to be very, very fast. So look at the ions under consideration. There are about 3 ions here. Look at the first ion. The first ion is N3 minus. That's the first ion. The second ion we have here is NO3 minus. NO3 minus. The third ion we have is BF4. They've repeated it again. Okay, sorry, it's not this one. This is another one. BF4 minus. That's another ion there. So we are expected to draw these 3 ions here and check their structures and also state the hybridizations of a central atom. So it's divided like this. So let me draw this out. Let me put this here. These are the ions. Now, what you have here is going to be their structure. Structure. Then the next thing I have is central atom. That's the central atom. And then I have the hybridization. So hybridization, central atom. Then what I have here is structure. Okay, so now since you know how to draw, Lewis structures, so the central atom for here is nitrogen. So you have nitrogen, or you know what? Let's draw it together. Let's not waste too much time. Let's draw it together. Now, if we say N3 minus, what is the central atom here? Oh, sorry. How many valence electrons are there in N? Not equal to 15. Now, there's a minus sign, right? So you say +1, which is equal to 16. All right, making sense. So central atom is nitrogen. then the other nitrogens are beside it. So place an electron pair in between each of them. So after placing the electron pair, what's the next thing you're going to do? Distribute the remaining valence electrons around the terminal atom so that they can attain octets. So I'm just doing that now. 1, 2, 3, 4, 5, 6. So I have 8. So let's count how many electrons we have. So 8 plus 8 is equal to 16. So we have 16 electrons. So we have used up all the electrons we started with. But this central atom here has not attained octet. What do we do? So we have to initiate a pi bond by cleaning 2 electrons from here and putting a double bond here. Cleaning 2 electrons here, putting another double bond. So this could be a possible Lewis structure for this. So you have N, double bond N, double bond N. All right. So 1, 2, 3, 4. 1, 2, 3, 4. So this is a possible Lewis structure for this particular species with a charge. Okay. Now we have that, the structure, let's draw it here. So we have N, N, N. It's already straight, so we don't care, it's straight. All right, so complete it. Okay, so that's fine. Now, what's the central atom here is what? Nitrogen. What is the hybridization of the central atom? Now look at the central atom. Don't forget that anytime you have 2 electron pairs around the central atom, it is going to be sp hybridized. Don't forget that in VSEPR model, we count a multiple bond as a single pair. So the multiple bond here, please, can you all hear me? If you're hearing me, say yes, I can hear you. Someone is saying I'm not hearing you. If you can hear me, please say yes, I can hear you. I want to know if I'm audible enough, please. All right, beautiful. You can hear me. Okay, so now central atom is nitrogen. Then the hybridization here is going to be depending on how many electron domains you have around the central atom. So the nitrogen here has 2 electron domains. So you can say it has 2 electron pairs. Now don't forget, under molecular geometry or VSEPR theory, we count 2 pairs of electrons, or let me say we count a double bond as a single pair. So how many pairs are here? 1 and 2. So therefore, because of that, this is what? sp hybridized. Let's draw the second one. This Lewis structure has been drawn in my previous video, but let's draw it again. So you have N, O, O, and O. This is Lewis structure here, minus. Now, from this Lewis structure, how many pairs of electrons are there around the central atom? 1, 2, 3. And because of that, since you have 1, 2, 3, this molecule is going to be sp2 hybridized. sp2. Sorry. I think my phone is having issues. Sorry. I need to plug this. I didn't even know it was not plugged. Oh my god. Oh, sorry. Okay. I think I'm back now. Okay, yeah, I'm back now. Let's carry on. Okay, so you can hear me, right? Can you all hear me? All right, you can hear me. So let's carry on. My battery was almost getting off. So let's figure out this particular one. So you can see that there are 3 electron domains here, 1, 2, 3. So because of the 3 domains, we are going to say that the hybridization around the central nitrogen atom is going to be sp2. So it's going to be sp2. So central atom is nitrogen, and it's going to be sp2. So let's draw the Lewis structure here. It's going to be N, O, O, and O. You can box it if you like. It's still fine. It's not that bad. So you complete the dots on the terminal atoms. It's very important to do that. Okay, so let's carry on. So let's draw for the next one, which is BF4 minus. BF4 minus. BF4 minus. Central atom is going to be B. We have B, yeah? Central atom B. Then we're going to have F, and F. Close this, put a minus outside. Now this is our Lewis structure for BF4 minus. I've drawn this before, that's why I'm not wasting time to draw it. So you can go back and draw it. Boron is in group 3 plus, fluorine is in group 7. 7 times 4 is 28. Then there's a minus sign here, plus 1. That gives you total of 32. So if you draw the Lewis structure, this is how it's going to look like. Don't forget, it's going to look just like this. So because of that, we are going to conclude that our central atom in this case is going to be boron. Oh, sorry. I just missed. That's a mistake. Central atom is going to be boron here. And the hybridization is going to be sp3 because it has 4 electron domains. 1, 2, 3, and 4. So it's sp3. So the Lewis structure remains B, F, and F. So you can close it in square brackets and put a minus sign outside. Don't forget, it's very important to complete the dots for the fluorine. All right, complete those dots there. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Please do a very nice job. Do a very nice job there. All right, I think we are done with question number 2. Let's go to the next question. Now, who has questions to ask under this segment? If you have questions to ask under this segment, please, I will love to. Yes, someone is saying that is the live video going to be here? Yes, I'm going to make sure I make it available. It's going to be available. Yeah, it's going to be available. Don't worry, it's going to be available for those that we are not able to, come online. It's going to be available. Yeah. Okay, so let's carry on. Let's carry on. So let's now go to the next question. Now, look at this. This one is very, very easy. The next question says, because lone pairs are larger than bonding pairs, lone pair interactions are greater than lone pair bonding pair interactions, which are in turn larger than bonding pair interactions. Using this notion suggests how the following species would distort from regular geometries. All right, so I'm answering the next question now. How the following species would distort from regular geometries. I want to be very sure I'm on track. All right, now check this out. I want to believe you have this in your manual. Check this out. Let's see how these species are going to deviate. Are going to what? Deviate. So how do we answer this question? Let me go through it again. It says, because lone pairs are larger than bonding pairs, lone pair interactions are greater than lone pair bonding pair interactions, which are in turn larger than bonding pair interactions. Using this notion suggests how the following species would distort from regular geometries. All right, these questions are kind of confusing, but I'm going to make it clear to you. So how are we going to answer this question here? First things first, we have OF2. Now, how does OF2 deviate from the original? Now, don't forget that OF2 looks just like this. So you can just draw OF2 structure just beside it. So let me draw it on my table. So this OF2 here. I want to believe you're following this. So this OF2. OF2. That's OF2 there. So I'm trying to draw it. So you're going to draw OF2 molecule behind it. You're going to draw O here, F, and what? F. Check this out. Now OF2 looks just like water. It looks just like water. It looks just like water. So if you follow up how to draw Lewis structures, you will notice that it looks just like this. F2. I'm coming. Let me draw the second one, which is S. Cl2. Sulfur is at the center, Cl by the sides. I'm drawing the way it should be. So this is SCl2. You have two lone pairs of electrons on the sulfur atom in this case. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, this is the Lewis structure for SCl2. Then what about PF3? Now, PF3 looks just like this. You have PF3. Now, you have P at the center. You have F. If you've been attending my classes, I've drawn all these Lewis structures. And if you've been watching my previous videos, I have drawn all these Lewis structures. I have drawn all of them. All right, there's a lone pair here. All right, so this is for PF3. Now let's now answer the question. Now the question is asking us, I will suggest how the following species will distort from regular geometries. Now, simple, straightforward answer. Now, you write the OF2 molecule will assume a bent geometry due to the presence of two lone pairs as opposed to its tetrahedral form. Put a full stop there. Now you're going to say that the OF2 molecule will assume a bent geometry due to the presence of two lone pairs as opposed to its what? Sorry, there's a mistake there. Its what? Tetrahedral form. All right. Let's check this out. We are done with this one. Now let's now go to the SCl2. Now, do you know that the SCl2 molecule looks just like the OF2 molecule? They look just alike. So the same reason you gave here, you're still going to repeat that same reason here. I'm repeating that same reason here. So now I'm going to say that the SCl2 molecule, I'm saying the same thing. The SCl2 molecule is bent. I'm changing my grammar a little. Is bent in shape due to the presence of two lone pairs. Due to the presence of two lone pairs, as opposed to its tetrahedral form. Now, what about this one here? That's the PF3. What are you going to say about the PF3? Now, you say the PF3 molecule is trigonal pyramidal in shape due to the presence of a lone pair on the P atom as opposed to its tetrahedral shape or form. All right, so I'm done with that. So we are done with question number what? Question number what? We are done with question number. All right, let's go to question number 4 now. I don't have question number 4. So once you send question number 4 to my WhatsApp, I don't have question number 4 here. Okay, don't worry, I have it. I've seen it. Don't worry, I've seen it. So question number 4 says, there are several families of hydrocarbons, among which are alkenes, alkanes, alkenes, and alkynes. The parents of each family are CH4, okay, the other one there, and the other one there, ethyne, respectively. Predict the geometries of these molecules. Give the hybridization of the carbon in each molecule and suggest whether they are polar or non-polar. They can never be polar because they are hydrocarbons. But let's just do that. They can never be polar. They are hydrocarbons. All right. So now let me draw the table for you. Let's answer the question together. Let me draw the table for you here. We're almost rounding off. I think we have barely 10 minutes or 15 minutes to finish this. We have barely 10 minutes or 15 minutes to finish. Okay, so now look at how to do it here. Now, this is our table. We have CH4. We have CH4. We have CH4 here. Then we have hybridization. Now for CH4, okay, we have the hybridization here. We have the hybridization for CH4. Then we have the yes or no. This one is very simple. Polar in bracket, yes or no. Okay, so now have you drawn the Lewis structure for CH4 today? The answer is yes. Now, when we drew the Lewis structure for CH4, it was just like the CH, H, H, and H. Around the carbon atom, there was no single what? There was no single lone pair around the carbon atom. Obviously, this molecule is what? Non-polar. So, polar, yes or no? The answer is what? No. It can never be polar. So, what about the hybridization? As far as this carbon has 4 domains, 1, 2, 3, 4. The carbon atom is what? sp3 hybridized. Moving on now. The next molecule there is C2H4. C2H4. Now, C2H4 is called ethene. Ethene is an organic compound. It's called ethene. Now, the ethene here, is it polar or non-polar? Now, look at ethene. Look at the ethene molecule. Look at the ethene molecule. You have C, double bond to C. H, and H. All right. Now, this is a ethene molecule here. Now, this molecule, the carbon atom you are seeing here, look at the carbon atom. Let me put an X. Look at the carbon atom, X. Now, this carbon atom, how many electron domains are around it? Let's count. 1, 2, and 3. Very simple. So, because it has 3 domains, 1, 2, 3, we are going to say that the central carbon atom, which is this carbon atom here, is what? sp2 hybridized. It has 1, 2, 3. So there are 2 central carbon atoms here. This carbon is central. This one is also central. So therefore, both of them are sp2 hybridized. So I'm going to write sp2 here. Now, polar, yes or no? Polar, yes or no? Let me see your answers in the comments. Polar, yes or no? Polar, yes or no? Check. Polar, yes or no? Let me see your answer in the comments. Polar, yes or no? Polar, yes or no? Yeah, it's not polar. Thank you. Polar, yes or no? Henry Onobon, no. Thank you. Precious Ebe, no. Conrad, no. Hope Water, no. The answer is no. Yes, it's not polar because the carbon atom does not have any lone pair of electrons around it. So the answer is no. Then the last one we are giving there is C2H2. Now, C2H2 is called ethyne. It's called what? Ethyne. Look at the ethyne here. Ethyne is C, triple bond to C. Then you have H. There are 2 central carbon atoms here. What are they? You have this carbon atom is central. This is also central. So this carbon atom here, how many electron domains are around it? Don't forget, in VSEPR model, a triple bond is regarded as what? A single bond. It's counted as a pair. So you have 1, 2. So this carbon has 2 pairs of electrons around it, meaning that the geometry for this molecule is what? Linear. It's linear in shape. So it's linear in shape. And the central carbon atom here is sp hybridized. sp. Now let's talk about the polarity. Yes or no? Is it polar or non-polar? What's the correct answer? Polar, yes or no? Teenager, the non-polar you are giving me, is it for the other one or for this one? All right, no. Henry Enobon, thank you very much. Is it Henry F. Young? Let me see. Sorry, Henry F. Young. Sorry, Henry Enobon, Esther F. Young. You guys are brilliant. Yeah, you're correct. So the answer is it is non-polar. So SP, the answer is no. So we are done with that problem now. We are done with that problem. So let's go to the next problem. The next problem says, calculate the formal charges of all atoms in NH3. Let me check this well. NH3, NO2, and NO3 minus. This question is kind of tricky because some of these structures here are going to have what we call, let me see, NH3, NO2. Is that NO2? Yeah, NO2. NO2 and NO3. So we are going to have quite some issues, but I think it's not really an issue. It's not really an issue. So this is the last problem we are solving for today. So what are the structures we are asked to find the formal charges on NH3? So let's start with NH3, NH3. Before you can find the formal charge on any atom in a molecule, you have to draw the Lewis structure. So I'm going to draw the Lewis structure now. Check it out. This is my Lewis structure. I have N, I have H, I have H, and I have what? H. Then there is a lone pair of electron here. All right. Now let's start by saying formal charge. What is the formal charge on the nitrogen atom? Let me write it, FCN. What is the formal charge on the nitrogen atom? It's going to be equal to, the formula for formal charge is equal to V minus B minus D. Please go back to my video on formal charge, how to calculate formal charge. Check it out. Formal charge is V minus B minus D, where V is equal to valence electrons. Now the B here represents number of bonds, and the D represents number of dots. So you have valence electrons. Now, when we say valence electron, we mean the group number of that particular element. The group number of that particular element is what we call the valence electrons. For example, nitrogen is in group 5. So the V for nitrogen is what? 5. Let me write the formula. V minus B minus D. All right. So for nitrogen is what? 5 minus. How many bonds are there around nitrogen? 1, 2, 3. There are just 3 bonds. 5 minus 3 minus. How many dots are there around nitrogen? Just 2 dots. 2. So the formal charge is equal to what? 0. All right. So I'm writing 0 there. 0 is my formal charge for nitrogen. Now you're going to do the same thing for the other ones. You're going to do the same thing for the other ones. So what is the formal charge on the hydrogen atoms? Now take note. Once I do the first hydrogen, I will not do for the rest because all the hydrogen atoms here are the same. So what is the formal charge for hydrogen? So formal charge for hydrogen is going to be equal to, so I'll start by saying hydrogen is in group 1. So it has 1 valence electron, 1 minus. How many bonds are there around hydrogen? It's only 1 bond, 1 minus 1. Do you have any dots here? No. So the answer is equal to what? 0. So therefore, each of these atoms here will have a 0 formal charge. Very, very simple. Very, very simple. So we have figured out all the formal charges on all the atoms in NH3. What about the formal charges of all the atoms in NO2? Now we are going to draw we are going to draw just one structure for NO2 because the truth of the matter is this. NO2 is expected to have about 2 resonance structures, or you should have about 2 structures that have some sort of double bonds. One of the structures should have a double bond, while the next one should have 2 double bonds. But we are going to draw the best Lewis structure here, which is this. So NO2, NO2. So NO2 is drawn like this: N, central, O, O. Then there's a single dot here, because the nitrogen is going to have, well, let me say this compound here has an odd number. That's an odd number of valence electrons. What do I mean by odd number? Let's check this out. Nitrogen is in group 5, 5 plus. O is in group 6, 6 times 2, 12. So total is equal to 17. 17 is an odd number. So it has an odd number of valence electrons. Please, sir, are we to answer questions on page 102? Let me see. Where is 102? Let me check my manual. 102. I don't think so. I did not get any information about that. I didn't get any information. But if you are to answer questions on 102, if I verify that tomorrow morning, then I will do it in class during my morning class by 8 a.m. All right, so let's carry on now. So this is the Lewis structure I'm going to be using. Now, this oxygen has 4 dots. This one also has 4 dots. Now, let's check whether we have 17 electrons here. Let's count. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. All right, we are going to be using this Lewis structure to calculate our formal charges. All right. Now, what is the formal charge on this oxygen atom here? Now, oxygen is found in group 6. So therefore, V minus B minus D. So for oxygen, V is equal to 6 because oxygen is in group 6. Now, B represents how many bonds, the number of bonds you have around that particular atom. Now, oxygen has 2 bonds around it. I'll say minus 2, minus. How many dots are there? 1, 2, 3, 4. There are 4 dots. Minus 4 equal to 0. So therefore, this oxygen has a 0 formal charge. This one also has a 0 formal charge because the 2 oxygen atoms are the same. They are both carrying double bonds. What about the nitrogen? Formal charge on nitrogen is going to be equal to V for nitrogen is 5 minus. How many bonds are there around nitrogen? Have 1, 2, 3, 4. There are 4 bonds here. 4 minus. How many dots are there? Just 1. Minus 1. So this is equal to what? It's equal to what? 0. All right. So the nitrogen has a 0 formal charge. So therefore, we are done with that calculation. Now let's do the last one. The last one here is NO3 minus. It's NO3 minus. So you have NO3 minus. Now we've drawn that today. NO3 minus looks like this. You have N double bond to O, single bond. Sorry, this is a single bond to O, single bond to O. All right. I think that pen is not writing well. Okay, so let's carry on. Let's continue now. So we have that. You have 4 dots here. 1, 2, 3, 4. Then here you have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now, if you want to calculate formal charges, make sure you've drawn your Lewis structures and completed all the octets of the terminal atoms. It's very important. Now, this is far different from the other ones we were doing, that we are neglecting those ones. Now, you don't have to neglect them anymore. You have to draw them. All right, let's calculate the formal charge. So what will be the formal charge on this oxygen that is carrying a single bond? Formal charge on oxygen is going to be equal to, oxygen is in group 6, 6 minus, how many bonds are there? Just 1, which is this, minus, how many dots are there? 1, 2, 3, 4, 5, 6 is equal to minus 1. So the formal charge on this oxygen is equal to minus 1, or just write minus there. All right. This oxygen is the same as this oxygen because they are both carrying single bonds. They are both the same. So I'm going to put a minus 1 here as well. Now let's now calculate the formal charge on this oxygen that has a double bond. Now, am I supposed to still do that? Because we just did that a few minutes ago. So the formal charge of an oxygen that carries a double bond is given as what? 6 minus 2 minus 4, which is equal to 0. So whenever an oxygen atom is carrying a double bond, the formal charge is always equal to what? 0. So the formal charge is 0. What is the formal charge? What is the formal charge on nitrogen? You have 5 minus, how many bonds are there? 1, 2, 3, 4. 4 minus how many dots? No dots. So this is equal to 1, which is plus 1. So it's plus. So the formal charge on nitrogen is what? Plus 1. Or just call it plus. Plus is fine. So we are done. This is how to do it. And this is all about this experiment. Please, if there's any question I've not answered on this experiment, please draw my attention on the comments. I want to see that. If there's a question I've not answered, draw my attention now, because I just answered the last question for today. Check. Check. I'm waiting for your response. If there's any question I've not answered, please draw my attention now. Let me see. Okay. I think, please, if I've answered all the, okay, preferred geometry for SF4, reason and dipole moment. Okay. Preferred geometry for SF4, reason. What does the D signify in the formula? David Christopher. Now the D signifies the number of dots. Now those dots you have around that particular element, those are the D, the dots. Yeah, it represents the dots. Now for Esther Basi, preferred geometry for SF4. Now the preferred geometry for SF4 is square pyramid. Sorry, seesaw. That's a mistake. It's seesaw. Check. We just did that a few minutes ago. Let me check for it again. Let me see. That's seesaw. I'm looking for that. Let me find it. Wow, where is it now? Wow, I can't find it. Okay, let me just go straight to the question. Okay, since I just found it now. All right, for SF4, the preferred geometry is square. Sorry, why am I just keep saying square? So the preferred geometry is seesaw. Seesaw. So why is the preferred geometry seesaw? I think that's what you're trying to ask. Let me get back to that question. SF4, preferred geometry is seesaw. Yeah, preferred geometry is seesaw or distorted tetrahedron. Reason due to the arrangement of electron pairs. Due to the arrangement of electron pairs. Then what again have I not done there? SF4. I think I already gave you a reason. I think I gave you 2 reasons. Although these 2 reasons are as a result of the dipole moment of that molecule. The 2 reasons are as a result of the dipole moment of that molecule. So I gave you, look at the first reason I gave you here. The net dipole is as a result of the lone pair on the sulfur atoms. Okay, you can use any of the reasons, that's fine. So the dipole moment here remains, where is it? Yeah, the dipole moment is yes. You can just put yes here. The molecule is what? Polar. It is a polar molecule. Please, sir, recap the reason for XEF4. Let me check. For XEF4. Now, for XEF4, what was my reason for XEF4? I can't find those books again. What was my reason for XEF4? I hope it's not this one. Okay, it's not this one. What was my reasons again for XEF4? Or it seems I just said it orally or verbally. I didn't really write it down. Okay, let me provide the answer. So for XEF4, the preferred geometry is going to be square planar. square planar. Now the reasons there, you can say the reasons is what? Due to the arrangement of what? Bonding pairs and lone pairs, according to VSEPR. That's a very good reason. I'm giving you variable answers now, so your answers cannot be the same. So the reason is because of what? The arrangement of what? The lone pairs and the bonding pairs, according to VSEPR model. Then for the dipole moment, you say the molecule is what? Non-polar. It has a zero dipole moment. The molecule is non-polar. It has a zero dipole moment. Simple. Don't go too far. So which other questions do you have? Let me see. That is, the double bond should be counted. Please, I didn't get you. Henry and Obong. Okay, yes. Now, in VSEPR theory, double bonds are counted as just a single pair. So, for example, if you should draw this molecule, which is called CO2, let me look for a new sheet. If you draw this molecule called CO2, now look at CO2 here. This CO2 molecule. Now look at CO2. You have C. This is the Lewis structure O. Now, if you are asked how many pairs of electrons are there around the carbon atom, how many pairs are here? Look at them, 1 and 2. So you count multiple bonds as what? A single pair. So that's how we do it in VSEPR model. Henry and non-bond, I just answered your question now. So double bonds are counted as 1. Even if you have a triple bond, it's counted as 1. I have a question here. The dipole cancel out due to the square planar reason for XCF4. Yeah, you can say that the dipoles cancel out due to the arrangement of what? Electron pairs in a square planar form. That's also a good reason there. More questions before we round up, because I need to shut down now. More questions. Please, sir, recap PF3. PF3. We've done P. Okay, look at PF3 here now. See, PF3 is on the screen now. Oh, yeah, look at PF3 is on the screen. Look at PF3. Check. So the PF3 molecule is trigonal pyramidal in shape due to the presence of a lone pair on the phosphorus atom, that's on the P atom, as opposed to its tetrahedral form. All right. More questions? Thank you, Dr. Benitex. Thank you very much. Sir, please, are we to write answers to questions on page 21? What's this? Which one is page 21 again? Which one is page 21, please? Which one is page 21? What's the geometry for XEF4? Now, the geometry for XEF4 is square planar. Now, check out this table you have here. Check out this table. Check out this table. Check out this table. Check it out. Check out this table. So XCF4, the geometry here is what? Square planar. Check it out. All right. So more questions. More questions. Sir, please, are we to, okay? What is geometry? Thank you, sir. Experiment 3. We've done experiment 3 before now. Experiment 3 is already on my channel. There's a video on experiment 3. There's a video on experiment 3. Check it out under solved problem. There's a playlist called solved problems. You see there, experiment 3, solved problems. All the problems on experiment 3 were solved there. So check it out. More questions? Sir, for the preferred geometry, do we need to draw the structures before writing the geometry? Is that question for which one? Let me see. Okay, I get your question now. Preferred geometry. There is even no now. For that preferred geometry, yeah, you can now listen to this. Check this out. Let me just correct this. I think something there. Because there's supposed to be a special column for drawing that before writing the preferred geometry. So what I'm going to do, like, draw the stuff on top. For example, SF4. Look at SF4 here. S, F, 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 and F, and that's all. Now under it, the preferred geometry. Remember, the column here is preferred geometry. So you simply draw it and now write the preferred geometry under it. So the preferred geometry here is what? Seesaw. All right. That's what you're going to do. Yes, that's how to do it. So write this, write it under it. Although the space is very small, but you're going to manage it. So we were asked to answer page 102. Who told you to answer page 102? Let me see. Page 102. Where is page 102? Okay, you are told to provide the answers to these questions here because nobody told me that. Nobody told me that. No, nobody told me that. So are we doing page 102? Have you confirmed it? I need a response. Have you confirmed you are doing page 102? Because I'm only seeing one person dropping that here. Okay, if you are asked to do page 102, then I'll provide a solution to that this night and drop it on the group chat. Yeah, I'll provide a question for that. Since you are saying you are asked to do it, I'll provide a solution for that and drop it on the group, or I'll post it on my channel. So let me start working on it right away. So this will be the end of our live for today. Thank you guys for coming around. Starting from Friday or Saturday, we are going to be having about two live sessions each to solve at least 10 problems from all the topics we've covered so far in class. Now, this is going to help us to scale through our exams coming up in the next months. All right, so I've seen a question. Please, the dipole moment of XCF4 is 0. XCF4 has a 0 dipole moment. It has a 0 dipole moment. Somebody said, sir, I've not answered the phase table on page 103 completely. The first 6 items. All right, okay, check it out. This should be page 103. Okay, check it out. This is page 103. So it's on the page now. This is page 103. Check. So while he's here, let me keep attending to other questions. Okay. So while he's there, I hope you are seeing it, right? So check it out. Let me check out other questions. Sir, please drop the link to the video on the group. I'll do that. Please, the dipole moment of XCF4 is 0. XCF4 has a 0 dipole moment. Take note. It has a 0 dipole moment. Okay, I'm attending to questions now. Sir, please drop the link of this video on the group. Yes, I'm going to drop the link. I'll drop the link. The video is even too long. Sir, please, how did you get the right structural formula for NO3? Now, what they wrote there, I want you to pay attention. What you have there is not NO3. What you have there is NO3 minus. It's not NO3. It's NO3 minus. Take notes. NO3 minus. All right. Okay, so please, we'll be ending our live for now. Let me power up my phone. I think my phone is about to die. It's about to die. So I'll see you guys in class tomorrow morning by 8 a.m. for those in town campus. So do have a wonderful night. If you have questions about this, you drop them on the video. I think I'm going to post the video tonight. Let me just work on it. So good night, everybody. Have a wonderful night. See you tomorrow. Good night, good night, good night, good night. See you guys tomorrow. I'm still seeing questions here. Don't worry, I'll attend to that later. So have a nice evening, everybody. Good night. Thank you very much. Yes.